Well, hello, welcome again to our journey into abstract algebra and number theory. And we've been looking at the structure of the U groups, and we saw how we could decompose some of these U groups into what we call direct products of subgroups. And we'll look at that again in a bit more detail later. But I wanted to move across now to look at these additive groups of Zn under addition. And when dealing with these, we have an analogous concept called direct sum. The two are really, obviously, as you'll see, very closely related, but I've separated them off as we analyse the U groups and then the Z sub n groups. So, motivated by what we've done before, we're going to take two subgroups of a group G written additively this time. And we're going to define the direct sum written in this way, A direct sum B, again to be the Cartesian product of A and B, with addition defined again component-wise. So when I add two ordered pairs, you simply add the elements in each position. So the direct sum of two subgroups again will be a group, and G will be isomorphic to this direct sum under the relabeling now of the ordered pair AB gets mapped across to A plus B, and it will be isomorphic precisely when the sizes of these, the product of the sizes of A and B is the size of G, and the only element in common is the zero element, which in general this will be the additive identity element. So the proof of all is exactly the same as that of theorem 2. Now we can generalize this notion of direct sum and later on of direct product of two subgroups to more than two subgroups by simply making this definition here. We're going to define this object to be the set of all k-tuples of the form A1 up to AK, where the A1 belongs to capital A1, A2 in capital A2 and so on, and you define addition in the obvious way, the same as we did back up here. So for example, if we have G is isomorphic to A direct sum B, and B is isomorphic to C direct sum D, then a typical element of this former structure here will be just the ordered pair AB, and then from the latter one here is going to be CD, and so the AB is then going to correspond to A and some element CD, and I'm just going to identify this object with simply the ordered triple, which is an element of A plus C plus D. In other words, if I can write B as a direct sum of C and D, then A direct sum B is isomorphic to A direct sum C direct sum D. Just as an example, if we take Z30, that is all the integers modulo 30 under addition, which are just the numbers from 0 up to 29, then I can take a couple of subgroups of this. These are the multiples of 5, these are the multiples of 6, and we can take a direct sum of these two, and it turns out that this direct sum, when you calculate this and you write all the elements out, you get exactly back to Z30. And this one here I'm going to write as Z6, or isomorphic to Z6. It's a additive cyclic group of order 6, and this is an additive cyclic group of order 5, and so I'm going to write this as Z6 direct sum Z5. Now immediately I hope you start to get excited here. We see Z30 is isomorphic to Z6 plus Z5, and of course 6 and 5 are just the product of these two numbers, and we'll come back and see how that works in a second. So just a note here, I'll write the additive cyclic group of order K as Z sub K, and I'm going to write the multiplicative cyclic group, as we were doing before, as C sub K. So note also, we could take this subgroup, the one we had up here, and this subgroup in fact can be factored further again, because this can be written as the multiples of 10 plus the multiples of 15. And that means then that I can I can factor this z sub 6 that we had up here into z sub 3 direct sum z sub 2. This is an additive cyclic group of size 3, additive cyclic group of size 2, and I can then factor this fully here. And again, we start to think about relatively prime numbers and factors, and you can see some interesting things about to happen here. Well, what's the isomorphism then that takes us, so these are isomorphic, what is the isomorphism that takes us from Z30 to say Z6 plus Z5? Well, you take an element n in this set, and we simply construct the element that's in this set, the ordered pair, by taking this n, and I read it mod 6 for the first entry, and then I read it mod 5 for the second entry. So for example, if I take 22, I read 22 is 4 mod 6, and 22 is 2 mod 5, and so this 22 in Z sub 30 corresponds to this ordered pair in Z sub 6 direct sum Z sub 5. Similarly, 15 is 3 mod 6 and 0 mod 5. Now you can probably see that something interesting is going on here to do with relatively prime factors. So the basic result in decomposing Zn is given by the following theorem. So this is our theorem 3. We take n to be the product of two integers which are relatively prime. Their GCD is 1. Then the result is that Z sub n is isomorphic to the direct sum of Z sub A and Z sub B, as you might have expected from the examples. Note also the converse is also true. That is, if we're given that Zn is isomorphic to this direct sum, and n is with n equals AB, then AB, these numbers must be relatively prime. I leave that as a little tutorial exercise. Just go through the proof of this. So we're going to define our bijection between Zn, our isomorphism between Zn and Z sub A direct sum Z sub B. Now what did we do? Well, we take an element x in here and we read it modulo A, and then we read it modulo B, and this gives us the ordered pair. One other way of writing this is to say we multiply x by the identity in this first set and x by the identity in the second, and this notation simply means I read x modulo A. It's just a convenient way, this is a convenient way of writing this in the proof. So firstly, psi is 1 to 1. Since if you've got two the same, then x and y are congruent mod A and x and y are congruent mod B. That means A, this one tells me A is a factor of x minus 1, this tells me B is of x minus y, B is a factor of x minus y. Now the GCD of these two is 1, and that means AB is a factor of x minus y, and that means n's a factor of x minus y, and that says x and y are the same mod n. Psi is also onto, since from the point of view of the sizes, the order of Z sub n is n, and the order of this is A times B, which is also n. So if we've got a 1-to-1 map between two sets of the same size, then it'll be an onto map. Finally, it preserves the structure. Using this notation I mentioned above here, then I can write psi of x plus y maps to this ordered pair, and I just expand this out, and I can write this as a sum of two ordered pairs, and that's just psi of x plus psi of y. So psi itself is an isomorphism. Now, as an immediate corollary to that, if I take my n and I can factor it in any way I like, and with these integers being pairwise coprime, that is, you pick any pair of these and the only common factor they have is 1, then Z sub n is isomorphic to this string of direct sums. So for example, if I take Z105, I can factor 105 as 3 times 5 times 7, and they're relatively prime, and so I can factor Z105 into this string of direct sums. I could combine these together, so Z sub 3 direct sum Z sub 5 is Z sub 15, or I can combine these two and get a Z sub 21, etc. Just in terms of subgroups, we can write Z105. I've written here that it's isomorphic to these three by the theorem, but what are the subgroups here? Well, I'm going to take I want a additive cyclic group of order 3, so I'm going to take the multiples of 35, and then I want one of size 5, so I'm going to take the multiples of 21, and then the multiples of 15, and these sets are all pairwise disjoint. The only thing in common is the 0 element, and so I can write this then as, in terms of subgroups, it's the direct sum of these subgroups. Well, all of this is all very sort of interesting in some ways that you can factor it, but so from a group theoretic point of view, this is very interesting, but what does it do from the number theoretic point of view? Well, in fact, it's going to give us a lovely result, which was known long before the group theory side of it, which of course is the Chinese remainder theorem, and I'll cover that in the next video.